Okay, today I'm going to talk about the frequency response curves used in EEG, kind of what it is, filters that go along with it, and I'm going to try to explain it as best as I can. Frequency response curve. The goal is to depict how a particular filter will impact or affect a particular frequency. So, by using a frequency wave curve, you can determine how much of the waveform's actual amplitude will be seen and how much of the amplitude will be attenuated or cut off with the application of a low frequency filter or a high frequency filter, a 60 hertz filter. So, in the EEG world, there are a couple common filters, mainly that I just mentioned: a low frequency filter, a high frequency filter, and a 60 hertz filter. So the goal of a filter is to be able to filter out all of the unwanted signals that we're picking up on the EEG, which happens quite a lot. The main goal of your test is to get a clear test with as little artifact as possible, and sometimes achieving that can be a little hard. That's where filters come in, and being able to use the frequency response curve in order to determine how much of your waveforms will be cut off, attenuated, or how much of your waveforms will be seen is important. A good example is maybe if you've been in a clinical setting doing a hookup on a kid and they're squirming around in the chair, you're getting a lot of muscle artifact. Applying a filter to that would allow you to see more of the true waveform from the brain rather than all of the squirming, the moving, the not holding still. So that's one example of when a filter and using a frequency response curve can come in handy, which I know probably everybody has come across that. Another thing is that it can be a little confusing knowing that the filters go hand in hand with the frequency response curves, but also the low frequency filter and the high frequency filter. It's a little tricky, and I'm still learning how to memorize it in a way that doesn't get confusing, because I feel like the more you read into it and the more you try to memorize certain definitions that may word it just a little different, it can be kind of confusing. So I got this from an ASSET Lesson 5, EEG 206. That's a little print off in one of our courses. So low frequency filter, high frequency filter normally go by their abbreviations of HFF, high frequency filter, or LFF, low frequency filter. So the low frequency filter filters slow potentials, allowing faster potentials to pass through. So a good way to think about this is like you're kind of like putting a wall down. You're blocking the slow potentials through coming through, only allowing faster potentials to pass unaffected. So the high potentials that would pass unaffected would hopefully be your brain waves that you want to see. They're also called high pass filters. So going back to my analogy with that, high pass. So you're letting the higher or faster potentials pass through while kind of putting a little block on the slower potentials. That is low frequency filter, LFF. High frequency filter filters the fast potentials and allows slower potentials to pass through unaffected. So this filter is also called low pass. So high frequency filter, low pass, low frequency filter, high pass. High pass. See, I start talking about it and I start thinking about it and I confuse myself, but remembering low frequency, high pass. High frequency, low pass. So, yeah, and it's important to know with the frequency response curves, like, obviously you don't want to botch your waveforms because you wouldn't have a clear test. So knowing how either a low frequency filter or a 60 hertz notch filter or a high frequency filter affects the waveforms that you're getting is really important, because the main goal is to find or to establish a clear, as much as possible, artifact-free record. So hopefully my frequency response curve was a little bit helpful, and that's all I've got today.